So let's take a quick look at motion of charged particles in a magnetic field. But first, let me talk a little bit about the third dimension that we're going to be looking at. Because our force and velocity are in very often different directions, say x and y, how do we represent the z direction in a diagram? Well, vectorially, if you look at this picture right here, you're going to see these little x's, and it says that's the direction of the magnetic field. This little x means we're looking at the tail feathers of a vector arrow that's pointing into the page. If we had a magnetic field that was coming out at us, then we would draw it kind of a circle with a dot into it saying that it's coming out of the page. You might also just see just a straight up dot. Similarly, you might see an X with a circle around it. That's just kind of some notation to keep in mind when you're looking at pictures in this chapter. So because the velocity, magnetic field, and forces are all in perpendicular directions, a charged particle moving in a magnetic field is always going to move at a constant speed. You can look at this and convince yourself that the velocity crossed with the magnetic field is going to be in a direction that's perpendicular to the velocity, so it can't change the magnitude of the velocity vector, just the direction. So what that means is that the particle is essentially going to be going around in a circle. And we could even use, some Newton's second law. Remember that guy? Sum of force is equal to mass times acceleration is equal to the force. This is going to be the magnetic force. And that's just going to be charge, velocity, magnetic field multiplied by the sine of the angle in between them. It's going to be 90, so it's just 1. This is going to be a centripetal acceleration. So mass, velocity squared divided by radius must be equal to the charge, velocity, magnetic field. You can solve this guy for r and figure out the radius of the circle with which that particle is going to go around in. The number of revolutions per second that it makes is going to be called the cyclotron frequency, and you might see that if you read up about some radiation physics. If the particle happened to have some velocity that was in the same direction as the magnetic field, some parallel component of it, again, the force is not going to be in that direction, and so we're going to have some helical motion, keeping in mind that the speed is not going to be changing, thus the kinetic energy of the particle must remain a constant. If we happen to have a magnetic field that was not going to be uniform, then we're creating what's called a magnetic bottle. You can kind of see how the magnetic field is changing in between these two coils, and all the forces are going to point towards the center of this bottle. So essentially, particles over here are going to go towards the center, particles over here are going to go towards the center. Essentially, they're going to resonate back and forth. We can see this on Earth, where we have Van Allen belts which protect us from sun's radiation, or highly charged solar wind coming off of the sun. And these act like traps for protons, and these protons undergo helical motion. We'll never actually, very rarely will we see these at our latitudes. We'll see the interaction of the charged particles with the atmosphere only at the north poles and south poles, although I have actually seen the aurora borealis in Maryland. So let's talk just very briefly about some applications of these forces on magnetic fields. Well, suppose we have a cathode and we can produce charged particles. It turns out that the speed of the particles is going to vary quite a bit. Suppose we only want a certain speed of particles in our beam. Well, we can use the electric force and magnetic force to create what's called a velocity selector. What this is going to use perpendicular electric fields. The electric field is going in this direction. We're going to have a positively charged particle, so it's going to feel a force in the direction of the electric field. Here we have a magnetic field, and the particle is moving with some velocity. The magnetic field is into the page, the velocity is down the page, so the force is going to be in that direction right there. We can essentially balance out the electric force and the magnetic force and say QE is going to be equal to charge times velocity times magnetic field. Cancel those charges out, and we can write that only particles that have a speed of electric field, or have a speed of E divided by V, are going to pass through without undergoing some deflection in one direction or the other direction. and we can control E and B fairly well, so we can select particles with only a certain speed for whatever application we're using. Probably the most famous use of the velocity selector is going to be Thomson's E over M experiment, where he measures the ratio of the object or electron's charge to its mass. Essentially, he had a cathode here and an anode here, so we had some potential difference across these guys. And what he did is he said, well, I know that the kinetic energy gained, 1/2 mass velocity squared, is going to be equal to the charge of the electron multiplied by the potential difference across these guys. Then I go through a velocity selector right here. So this velocity selector said that my velocity is going to be equal to my electric field divided by my magnetic field. Same type of deal. I have a magnetic field here, electric field here. Now I've selected only certain velocities, and I can look at the impact of these electrons on a screen, measure the deflection, and I can use the fact that these two velocities must be the same to determine the the charge per unit mass, knowing my electric field and magnetic field. A far more useful application in the real world, and we did use these at NASA, was a mass spectrometer or a mass spec. Essentially, it allows you to measure the mass of various ions and determine what we're looking at, in our case, in the atmosphere. So we would be shooting out charged particles. If we knew the charge we put on those guys, and they go through a velocity selector right here where we control E and B, then it's going to enter a region of uniform magnetic field, where we could say that the force is going to be equal to the charge times the velocity times the magnetic field, and we're going to say that's equal to the mass velocity squared divided by the radius. So it's going to be uniform circular motion once again. What is going to happen is in this region right here, the particles are going to curve. How much they curve is going to depend on their mass. So if I know the charge on them, I've used my velocity selector. I know what magnetic field they're entering. I know how fast they are because of, again, velocity selection. And the radius that they travel, measured by the particle detector, is going to be related to their mass. And I can tell you whether I'm looking at sea salt or smoke, because they're going to have very different masses. Since currents are just charges that are moving, we know that we can write current as being equal to some flow rate of charge per unit time. It makes sense that if we have a current carrying wire, there's going to be a magnetic force on this guy. Remembering that force is equal to Q V cross B, you can easily convince yourself that the force is going to be equal to the current I multiplied by the length of the wire, or the direction of the length of the wire, crossed with the magnetic field. And what we do for the direction of L right here is we choose L to be in the same direction as the current, and we use our right hand rule, crossing the current direction into the direction of the magnetic field, getting our force. We can also write the magnitude as ILB, sine of the angle in between them, much like we did for the cross products earlier in this section. One use of the fact that a current carrying wire is in a magnetic field is going to experience a force would be in loudspeaker design. If we took some very, very light wire and looped it around into what's called a voice coil, and we hook this guy onto a piece of material, a speaker cone, and we put that guy into a magnetic field created by permanent magnets. We put all those guys together, we have the magnetic field due to the permanent magnets, and we have a current flowing through this voice coil. As someone's voice is going to go up and down, then that current is going to go from essentially positive to negative as a function of time, causing that current to change direction, causing the force to change direction, therefore causing this membrane to go in and out as the force changes back and forth with the current. So let's just take a quick look at using this equation for force and current following example 27.8 here. So here we have some current flowing along a semicircular path and then a straight path. and we're asked for what's the force on this object. It's sitting in a magnetic field. The magnetic field is pointing outwards, so you see the little dots right here. What we can do is we can break this up into the two parts, figure out the force for that part, figure out the force for that part, and then essentially just add them together. The force for the first part is pretty straightforward. It's going to be the current multiplied by the length crossed with the magnetic field. You can kind of look at this guy, see the current flows in the same direction, or L flows in the same direction as else, or is in the same direction as current, so in that direction. You cross those guys and you get your force is just equal to I multiplied by length multiplied by magnetic field, and the right hand rule gives us the j hat direction. Now for force number 2, or some d force level 2, you look at tiny little chunks of this rod there with length dl. The dl hat direction is going to be tangential to the circle right there, and so here we're going to have current dl crossed with magnetic field. Again, the right hand rule is going to say this is going to be I dl multiplied by magnetic field, kind of in some r hat radial direction. What we can then do is say, well, I know that dl is just r d theta, and I can also break this guy up into my x and y components. And what I want to do is I want to say, alright, my force 2 in the x direction is just going to be the integral of all those tiny little forces right there. I can simply write this to be the integral from 0 to pi. I'm integrating up over all my angles, so starting at 0, finishing at pi. And that's going to be equal to I r d theta multiplied by b. And then since I'm just looking at the x direction, that's going to be this side of the triangle right there, cosine theta. So that's going to give me some current, my radius, my magnetic field, multiplied by negative sine theta evaluated at 0 and pi. That's just going to be equal to 0. Do the same thing for the y direction, only now we're tacking on a sine theta. So that's going to be equal to I times r times b, integrate up 0 to pi of sine theta d theta. And that's just a cosine theta evaluated at 0 and 2. So we're going to end up with 2 IR magnetic field. And this is in the y direction, so also in the j hat direction. And so for the net force, we simply add that force to this force. Another way to look at it very briefly is to consider current flowing around a circle in a uniform magnetic field pointing upwards. Obviously, if you kind of add these forces up, you have a force on that wire, a force on that wire, similarly one here and one here. The net force will be equal to 0, however we can generate a net torque that is not equal to 0. Now we can talk about this torque that I just very briefly talked about in the last page to be equal to the cross product of this little mu guy, which is going to be the magnetic moment, which is essentially going to be very, very similar to the dipole moment that we talked about for electrostatics. And this magnetic moment is going to be equal to the current flowing through the wire multiplied by the surface area of the wire. And to find out its direction, you're going to take your fingers and curl that in the direction of the current, and look at the direction that your thumb points. That's the direction of this magnetic moment. This concept of a magnetic moment also allows us to talk a little bit about the potential energy of a magnetic dipole and a magnetic field. This potential energy, I'm going to call that U, is going to be equal to negative of the magnetic moment dotted with the magnetic field that this dipole is in. So this lets us talk very briefly about how magnets work. What we can do is we can take our, say, a given piece of iron, we can break it up into little tiny slices. These are actually called domains, and we treat each one of these domains as a loop with current flowing through it, and then a magnetic moment. For an unmagnetized piece of iron, these magnetic moments are going to just point in random directions and essentially cancel each other out. In a bar magnet, all of these magnetic moments are aligned, so here they're all pointing towards the north for each and every single one of these little domains. That's going to give us a net magnetic moment in that direction right there, and if we put this magnetic moment into a magnetic field, there's going to be a net torque acting upon this guy, on this magnet. All of this is going to boil down to how a direct current motor works. Here we have a north side of a magnet and a south side, so we're going to have a net magnetic field in that direction. And if we have current flowing through this wire right here, we're going to set up a magnetic moment, we're going to set up a torque, and the net force is going to be upwards over here and downwards over there. That's going to cause this contraption to rotate. It's going to rotate 90 degrees, and we're going to have some contact with some contact that's not going to allow any current to flow through this loop, but inertia is going to carry this guy through the rest of his path. It's going to keep on going down. It's going to come into contact. Now we're going to have current flowing in that direction and in this direction, keeping the net forces to be up and down, essentially causing this shaft to spin round, and it'll be connected to, say, a wheel or a gear or something along those lines.